everyone, Katie O'Neill Kanasic here with yet another environmental disaster examined through the lens of analytical chemistry. Let's get into it. We're headed to, and I'm probably going to butcher this, but Norilsk, Russia, specifically the Norilsk nickel metallurgical plant and the nearby Daldican River. See right here? That's the Daldican River. Yep, gotta love that red watercolor. And yes, I said red, not really a normal watercolor. Something's definitely wrong here. So, what happened? Depending on where you look, you'll get different answers as to what caused the Red River. And while this isn't the first time the Daldican River went red, the biggest news coverage of it happened in September 2016, and the blame given to none other than the Norilsk nickel plant. Either a pipeline broke or a dike overflowed, but ultimately waste from this metallurgical plant escaped from the smelting confines and into the nearby river, turning it red. Almost comically, Norilsk Nickel put out a statement saying, "Short-term river color staining with iron salts presents no hazards to people or river fauna, and we will work to avoid such incidents in the future." Yeah, that's funny. But also not really. The Norilsk region of Russia, particularly around this metallurgical plant, is highly polluted. This plant, which provides significant amounts of copper, 1/5 of the world's nickel, and half the world's supply of the precious metal palladium, also contributes 2 million tons per year of acid rain producing sulfur dioxide. This plant is actually surrounded by a vegetative dead zone, complete with its own mud slurry. And this pollution doesn't come without heavy metals, especially since we're dealing with a metallurgical plant. Just in case you aren't convinced, these studies show that the Norilsk region of Russia is a very polluted region. Why am I telling you this? Well, particularly because the statement that Norilsk Nickel put out wasn't entirely wrong. What turned the water red is in fact iron salts, and a bit of iron in your water isn't going to kill you. But the fact that Norilsk Nickel claims that there are no hazards for people and river fauna, yeah, that couldn't be farther from the truth. Let's take a look at the chemistry behind iron turning the water red, and how big this problem really is. The specific substance that makes water red is ferric iron, which is oxidized from ferrous iron. Once oxidized, the iron will precipitate as iron hydroxide. So how does this oxidation occur? The redox reaction for iron can be written as such: 2 iron plus oxygen plus proton into iron 2 plus and water. Let's write the half reactions for these, shall we? So the reduction reaction occurs with oxygen. Oxygen plus proton plus electrons into water. And the oxidation reaction, of course, with iron. Iron into iron 2 plus and electrons. This only produces iron 2 plus ions, however, and requires a bit more chemistry to make the red precipitate we're looking for. A second redox reaction occurs as follows: iron 2 plus oxygen plus proton into iron 3 plus and water. The oxidation of iron looking like this: iron 2 plus into iron 3 plus electrons. Now, doesn't that equation look a little bit familiar? Finally, these iron 3 plus ions can combine with hydroxide ions in water to then form the iron hydroxide compound we're looking for. That can dehydrate to form Fe2O3 times some multiple of water, which is the formula for rust. Yep, that's right. You can technically say that the Daldican River water is rusting. Using more of our knowledge from quantitative analysis, we can say that the iron solid initially in the solution is the anode, as it is being oxidized, and the oxygen within the water is the cathode, as it is being reduced. Therefore, we get electrons leaving iron and moving into water, which in this case just makes more water, and we precipitate out the iron hydroxide. So we get it. With our knowledge of redox reactions, we can understand how iron waste from the smelting plant turns into rust when it hits the water, therefore making the water run red. And our are we done here? So, you all remember this graph, right? Straight from our textbook. The solubility of metal ions is reduced at low concentration of ligand, but can be increased as the ligand concentrations increase, allowing for various complex ions to form. For this scenario, iron contributes to the metal ions and water acts as a ligand, thus forming a metal-aqua complex ion. And so iron is acting as a Lewis acid, while water acts as a Lewis base. We can generate a hexaaqua iron 3 ion, where iron is surrounded by 6 water molecules. This is a very acidic substance, but as it interacts with water molecules, it neutralizes, and we get the same red precipitate. Take a look at this video from Chemistry LibreText, which shows a solution of the iron complex precipitate dissolving with added hydrochloric acid back into that very acidic hexaaqua iron 3 ion, which will look dark greenish, and reprecipitating with the added sodium hydroxide back to red. So depending on the pH, with more acidic conditions, we won't see that red precipitate. But as they get more basic, we start to see the iron hydroxide. Now we have two possible ways to explain the reddening of the Daldeccan River: the redox reaction and the acid-base chemistry. And it's not impossible that both of these aren't happening at the same time. Studies have actually looked into which species dominate at which pH and which redox potential. You can see the specific species we were talking about too, the iron ions, the result of the complex ion formation. And in this study, which shows a slightly different graph, you see the result of the redox reaction. But we haven't answered our original question yet. How big of a problem is this? Iron, as you may already know, is necessary for our growth and development. It makes hemoglobin for our red blood cells to carry oxygen. It's a component of some hormones. It's important for our immune systems, our hair, our nails, our skin, and plays a role in converting blood sugar to energy as well. Essentially, we really need iron. The thing is, we don't need that much. If we were to take a sample from the Daldeccan River and run an atomic absorption spectra on it for the iron absorbance, and then do a bit of standard addition, just like that face-to-face Lab 6, we would find our stock solution of the Daldeccan River water to be significantly concentrated with iron. Remember how we talked about how polluted the Norilsk region is? And how many heavy metals are found in that region? One known fact about heavy metals is that they're highly soluble in acidic environments. Now, let's go back to those graphs of the different forms of iron. You can see that both the redox version and complex ion version are present in acidic environments. And while the redox potential may vary which species dominates, the point being, they can exist in acidic environments. That means that heavy metal ions can easily dissolve into the water and travel down the stream, potentially depositing farther away from the smelting factory and destroying vegetation there. Or just simply killing aquatic life as they remain soluble in the water. Is there a solution? Unfortunately, chelating effects, activities, complex ion formation, yep, all those topics we know and love from quant, will cause heavy metals to stay in solution for longer than expected. And as a result, it can more easily subvert any water filtration or cleaning procedures. The methods by which the Norilsk Nickel Company operates needs to be updated. But with more knowledge about this topic, and with taking classes like quantitative analysis, we can better understand the chemistry going on behind these environmental phenomenons, and may be able to work our brains and determine some sort of solution to this. Thanks for watching.